In this video, we're going to be taking a look at something called the common ion effect. So I want you to make a prediction before we do this calculation or this example here, and then we're going to test your prediction out. Suppose I have two beakers. Let's go with they have the same volume of water. We'll call this beaker A, and this one beaker B. And suppose we want to dissolve some calcium carbonate, just because we used that in the previous example, some calcium carbonate in each beaker. Let's say that beaker A only has pure water. But beaker B actually already has other ions in it. Beaker B has water plus, I don't know, some calcium ions already in there. So there's already some calcium ions here. In which of these beakers would you expect to be able to dissolve more calcium carbonate? In the beaker that contains only pure water, or in the beaker that contains pure water and already some calcium ions? So make your prediction. So predict. A or B, which can dissolve more? The beaker B or beaker A. And then let's go and do a calculation to see if we can support or refute your prediction. Okay, so write your prediction down and let's go into a calculation. So here we have calculate the molar solubility of calcium carbonate in a 0.0010 mole per liter solution of calcium chloride. Okay, interesting. So we want to find the molar solubility of calcium carbonate. So usually when we want to find the molar solubility of something, we make a dissociation equation. And that's what we're going to do. We're going to make a dissociation equation. Just like this, just as we saw in the previous example. And we're going to make an ice table. Okay. And we're also going to write out the Ksp, because we know if we want to find molar solubility, we need the Ksp, which came from our table, our Ksp table. And in the previous question, we saw that to be 3.36 times 10 to the power of negative 9. So Ksp is equal to 3.36 times 10 to the power of negative 9. And if you want to write a Ksp expression, you would simply do Ksp is equal to the concentration of your two ions multiplied by each other. And none of them are squared because there's no coefficients, but if there were, you'd have to keep that into consideration. Okay, now how is this a little bit different from the previous question? But notice the question is saying here that you have 0.001 mole per liter solution of calcium chloride. So this question is a bit different because you don't start off with 0 of each of the ions. You'll have 0 of the carbonate, but not 0 of each of the ions. You have some calcium in the solution already. So we need to go figure out what is that value of calcium in the solution. Remember, you're told that you have calcium chloride. That's what you're told. Okay? And you're told that that's completely dissolved into the water. So you already have that concentration there. So I made a dissociation equation to show calcium chloride. I had 0.0010 molar, or moles per liter. And I made a balanced dissociation equation, so 2 here. So I could find the concentration of each ion. Assuming all of this dissolved, then all I have to do is a molar stoichiometry to find a concentration of each ion. So this and this are in a 1-to-1 ratio. So what that means is I have 0.0010 molar calcium. And then this and this are in a 1-to-2 ratio, so I have 2 times that, so 0.002 molar of chloride. But I don't really care about the chloride ions because all that I care about for my ice table for my calcium carbonate specifically is the calcium. So my initial concentration of calcium in the water is not 0. Because I have calcium chloride, it's actually 0.001. So 0.0010 molar. That's my initial concentration. And so what is the change going to be? Well, the change is going to be the same idea. We have plus X over here and plus X over here. And we're going to get over here 0.0010 plus X. So because we're dissolving more calcium carbonate, so we get more calcium. And then this is simply X. The reason carbonate is simply X is because we had 0 to begin with, and then whatever dissolves will then be our X value. And then the reason we have this over here is because we already have some calcium in the solution. So now we have some values here to help us find our MSP. Now remember, this is going to be minus X, and this is going to be 0 because all of this should dissolve. So once we find our X, we're going to find our MSP. So what do we know? Right now we know that the Ksp, so 3.36 times 10 to the power of negative 9 is equal to 0.0010 plus X times X. Now there is a bit of an issue here. If we expand this, we're going to get a quadratic equation, and that's fine. You could use a quadratic formula, but I do want to test my 100 rule out over here because I want to find X. So 100 rule, we'll do the initial concentration, 0.010, over the Ksp, which is 3.36 times 10 to the power of negative 9. And if you put that in your calculator, you're going to see that that's much greater than 100. So therefore, we can actually simplify that. We can remove this X. And so what we'll get is times 10 to the power of, that should be negative 9, not negative 19, is equal to 0.0010 times X. And so now we can solve for X by dividing both sides by 0.010. And we'll get that our X is equal to, so we do our 3.36 times 10 to the power of negative 9. We're dividing that by 0.0010. And we get 3.36 times 10 to the power of negative 6. So that's the concentration that we found. 3.36 times 10 to the power of negative 6. That's our X value. That's how much carbonate will be dissolved in there. And that's how much our calcium carbonate will change by, which is our MSP. So this is our MSP, and our sig figs is going to be 2 sig figs, so approximately 3.4 times 10 to the power of negative 6 molar. This is our MSP. So let's test our prediction now. This is the MSP when you have calcium chloride already in the beaker. That's beaker B. So it's 3.4 times 10 to the power of negative 6. 3.4 times 10 to the power of negative 6 molar. The example we did in the previous video was like beaker A, where there was nothing to begin with. So 5.8 times 10 to the power of negative 5. These are the MSP values. Notice that the MSP is higher in beaker A compared to beaker B. You have a higher MSP here compared to here. And so what that means is that our observation is that A can actually dissolve more. You can dissolve more calcium carbonate in the pure water compared to the water that already contained some calcium ion. And so what we've just demonstrated is something called the common ion effect, where your ion molarity does not begin at zero. You already have some of the ions of the compound that you're trying to dissolve in the solution. And so when that happens, you actually reduce the solubility of the compound. You reduce the molar solubility, reduces the MSP. And if you think about it, it makes sense. You already have some of this ion in there. So you have less room for that ion to come in. So you won't go, you won't be able to dissolve as much as you could have if you didn't have any ions at all. So because you already have some of this, the equilibrium won't lie to the right as much. It'll be more towards the left side in a situation like this because you already have a lot of the calcium ion dissolved in there. So the common ion effect, well, what is that? It reduces the MSP. It reduces how much of the substance that you can dissolve because you already have some of the ions there. Again, you only care about the ions that you have in common. So that's why I didn't care about the chloride here. I cared about the calcium specifically. So now you know that when you already have some ions dissolved in a solution, if they're ions common to the salt that you're trying to dissolve or to the ionic compound you're trying to dissolve, you'll have a lower solubility. You won't be able to fit as much in because you already have that beaker, that solution partly filled with some of the ions that are part of this ionic compound. And that is the common ion effect.